Good evening, everyone. Am I audible or not?
Sir, sir.
Right, sir. Just we will see for another 2 to 3 minutes, then I will start the lecture. Shall we start? I think only 29 joined. Okay. We waited for sufficient time to start the lecture now. See this? So we need to discuss about P block, in which for weekday students, I have already started 5th A group elements. Right? For weekend students, I have not yet started. So let me start with group 18 now. So today I will try to complete group 18. Then I will go to group 16, 17, then I will come to group 15, right? So today we will see group 18 elements. Right, sir. Now observe corresponding elements. Now what are corresponding elements of group 18? Or we also call it as 8th A group elements. We also call it as noble gases. Compared to this word noble gases, inert gases is more suitable. Right? Sorry, I think compared to inert gases word, noble gases word is more suitable because xenon is reactive. Inert gases mean they should not be reactive, right? So the word noble gases is more suitable than, this is more suitable than the word inert gases, because inert gases represents not reactive, but we have compounds of krypton to some extent. Xenon reasonably forms compounds with oxygen and fluorine, right? So these two elements can form compounds, right, with more electronegative elements like oxygen, fluorine. For example, if you take xenon with fluorine, it forms XeF2, XeF4, XeF6. Similarly with oxygen, XeO3, XeO4, right? With oxygen and fluorine, XeO2F2, XeOF4, Xe F4 if we take OF2, etc. Whereas the major reason for identifying that xenon is reactive is ionization energy of oxygen molecule and ionization energy of xenon are relatively same, right? Nearly same. So oxygen will form one compound with platinum and fluorine. We write as O2 PTF6. Similarly, xenon also is expected to form XePTF6 complex, right? They will say it as this is the first compound of xenon. Based upon that, they predicted reactivity of xenon with other elements like fluorine oxide to form other compounds, right? And while we study about noble gases, we need to remember names of two scientists. One is Ramsay and Rayleigh, because most of the most of the noble gases existence is predicted by these two scientists. Now coming to general electronic configuration. General electronic configuration of noble gases is NS2 NP6, general outermost electronic configuration. With an exception, helium. Reason, helium have 1s2 configuration. This is the only noble gas without p orbitals, have completely filled outermost orbit, that is first orbit, and less reactive. Hence, we call it as, or we are considering this in noble gases, right? Now, after helium, neon, argon, krypton, xenon, radon, oganesson. These are all noble gases, in which radon and oganesson, these two are radioactive. So you know that respective atomic numbers, 2, 2 plus 8, 10 plus 8, 18 plus 18, then 36 plus 18, 54, plus 32, 86, plus 32, 118, right? These are atomic numbers, corresponding electronic configuration, 1s2, outermost configurations I am writing. So helium core, 2s2, 2p6. Here 3s2, 3p6, 4s2, 3d10, 4p6, and so on. So I am writing neon, 3s2, 3p6, argon, 4s2, 3d10, 4p6, krypton, 5s2, 4d10, 5p6, xenon, 6s2, 4f14, 5d10, 6p6, radon, 7s2, 5f14, 6d10, 7p6. So this is electronic configuration of noble gases. Outermost configuration is NS2 NP6 except helium. No. Already we have seen these names of these elements are based upon the experiments and their identification and source. The word Helios means sun. So the name of helium is obtained from the word Helios, meaning sun. Similarly, neon meaning is new, neos. Argon, argos means lazy. Kryptos means hidden. Xenos means stranger. The radon is the word obtained from radium, element radium. So names of these elements are based upon the source, or when they are doing the respective experiments, whether we are able to find a new spectral line in the leftover material during distillation of air and so on. So which is not necessary as of now, right? So we are not bothered about their identification and isolation of respective elements. Are you following? Someone respond.
Yes, sir.
Right? And no need to discuss about their molecular orbital diagram, right? So if you see MO theory, all have bond order 0. That's why they exist as individual molecules, means monoatomic molecules. All noble gases are monoatomic molecules. Bond order 0. Right? Now, if you observe their melting points and boiling points, let me see that table for noble gases. I think table is given. Let me take the table. Say this. I'm talking about this table. So first we will discuss about all the data given in this table. Observe this. In which no need to discuss about atomic number, atomic mass is also increasing from left to right. Observe atomic radius also increasing, means down the group, not left to right, down the group, because all belongs to same group. Ionization enthalpy. Ionization enthalpy, if you observe, down the group size is increasing, therefore ionization energy is decreasing gradually. Electron gain enthalpy, very, very, very important point. While we are discussing periodic classification of elements, we discussed this point regarding electron gain enthalpy. Observe, exclude helium. Down the group, it is decreasing. So if you see electron gain enthalpy, neon is greater than, argon is approximately equal to krypton, xenon, radon, and helium. Helium is less positive. Electron gain enthalpy values of all noble gases are greater than 0. Electron gain enthalpies of noble gases is greater than 0. Right? So this is important thing we need to remember. So which is having highest electron gain enthalpy means neon. Now observe density. Here also there is a gradual change. So 1.8 into 10 power minus 4, 9 into 10 power minus 4, 1.8 into 10 power minus 3, 3.7, 5.9. So density is gradually increasing down the group. So density increases down the group. Here ionization energy decreases down the group. Now, melting point and boiling point. Observe melting point values. So when we see these melting points, we need to remember, along with noble gases, we need to remember melting point values of oxygen as well as nitrogen. Right? So observe melting point values of oxygen. Group, no, here itself we can check. Observe melting point values of oxygen. Melting point is 55, boiling point is 90. Right? In terms of Kelvin. So I'm writing the same. Melting point of oxygen, in case of oxygen, melting point is 55, boiling point is 90. In the same way, nitrogen. Observe this. It is 63 as well as 77.2. 63, 77.2. Now see the melting point values and boiling point values of noble gases. Now in case of helium, its boiling point itself is very low, 4.2 Kelvin, right? So converting helium to solid is practically impossible, right? Whereas if you keep on decreasing temperature approximately at around 2 Kelvin, it has a different behavior, right? So we call that as helium-2, right? We write that as helium-2 because of its peculiar behavior at around 2 Kelvin, right? So we are not able to discuss that part right now. So coming to melting point, observe the melting point values increases down the group. Melting point values increases down the group. But we need to compare that along with oxygen and nitrogen also. Now, if you see order, helium is less than because it is very low, right? Close to approximately close to 0 Kelvin, right? So that's why we have not mentioned anything. So melting point of helium is very less, or we can write approximately equal to 1 Kelvin, close to 0 Kelvin. Then neon. Then instead of writing argon, I am writing oxygen. Then nitrogen. After that, argon, krypton, xenon, radon. Same way if you consider melting boiling point, this also increases down the group. Here also I am doing comparison along with oxygen and nitrogen. So helium, then neon. After that, nitrogen. Then comes argon. Then oxygen, krypton, xenon, radon. So observe these order: neon, oxygen, nitrogen, argon, neon, nitrogen, argon, oxygen in melting point and boiling point occurs. Any questions are up to this? Someone
No, sir.
respond. Right. So melting point and boiling point values are very low because they exist as individual molecules, means monoatomic molecules. There are no interactions. Only van der Waals interactions, or we call them as London dispersion forces exist. Therefore, their melting point and boiling points are very low. Now, here also, one more point. While we are considering atomic radius, actually these atomic radius are van der Waals radius values. Van der Waals radius values. Generally, radius, what happens? Atomic radius in a period from left to right decreases. But if you observe these values are high in that respective period. Reason, for all other cases, we are measuring either covalent radius or atomic radius. But here we are measuring van der Waals radius values. That's why these values are high when compared to other elements of respective period. Any queries, sir, in this? This is also important point. When you practically observe that values, these values are more than expected. Clear? Respond. Do you have any queries in this up to here?
No, sir.
No, sir.
No. Next, coming to abundance. This is also important point. Atmospheric content percentage by volume means we are talking about abundance, availability. So abundance in atmosphere, not universe. I am considering availability in atmospheric oxygen in terms of volume by percentage by volume. So now observe these values. Helium, neon, krypton, xenon. I think something not matching here. Just a moment. Something is wrong here, man. Which year book this is? There is something wrong because argon is most abundant element in Earth atmosphere. But here they gave krypton. This is also old one, I think. This is nitrogen family. This is wrong. These are also wrong. Something wrong in this table. I think I have this new edition book. See, sir. Now it is correct. Observe abundance of noble gases by volume. So small modifications let me do. Now okay. Right? Now observe abundance, which is most abundant element? Argon, na? Respond.
Yes, sir.
So argon is most abundant. After argon,
Neon.
right? Then
Helium.
helium. Hey, that
Yes,
is
sir.
10 power minus 4, man. Neon, 10 power minus 3. Right? Then helium. After that, krypton, and comes xenon. Right? So argon is the most abundant noble gas when you consider atmospheric that means atmospheric in Earth's atmosphere, right? So its volume is approximately 1%. So all combined, their volume is approximately 1% of atmospheric volume, right? Almost negligible, right? Response, sir. Any questions in this?
No, sir.
No, sir.
No. One more point. Except radon and organism. Yes, sir.
Sir, in decreasing order only it will come, no, sir, abundance.
Oh, I wrote reverse, huh? 1 minute. Correct. Argon greater than neon, helium, krypton, xenon. Right. Now, coming to this. Except radon and organism, all are obtained from Earth atmosphere. In which radon is obtained from uranium ore. Whereas organism is synthetic element. Hello? Yes? Madam, yes, madam. Good, madam. Good, madam. How you are, madam? Right. So we'll continue. So what we are discussing in at the atmosphere, you will find all noble gases except radon and oganesson. These two are not obtained from air. Radon is obtained along with ore of uranium. Oganesson is man-made element, synthetic element. If we consider universe into consideration, if we take total universe in consideration, so in universe, most abundant element is hydrogen. Next most abundant element is helium. If you take Earth's atmosphere into consideration, or on the surface of Earth, which is most abundant element? Any of you? Which is most abundant element on Earth? While we are discussing S block, we have just seen this man. Most abundant element on Earth surface.
Aluminium, sir.
Aluminum is most abundant metal among metals.
Nitrogen.
Nitrogen at the atmosphere. You have to take Earth
Hydrogen.
crust also into consideration.
For oxygen, sir.
Oxygen. Second most abundant?
So silicon.
Yes.
Silicon, sir.
Silicon. Right. Third, aluminium. Fourth,
Iron, sir.
iron. Correct. Right. This is what we have seen in while we were discussing, I think, S block. Right. Okay. So let me continue. So if you take total universe into consideration, most abundant element is hydrogen, whereas helium is second most abundant element. One more point. From air, how we are going to separate noble gases means we have two methods. One is Dewar flask method, and another one is fractional distillation method, right? So by fractional distillation is the better method in order to separate noble gases from air. So by doing fractional distillation of air, after removing from dust, moisture, and so on, after freeing from dust, moisture, etc., right, we will get remaining gases, which on what we say it as we will liquefy them at liquid air temperature. Right after liquefying, we will slowly warm up, so which will convert into vapor. Those vapors, those gases will be separated. Remaining liquid was done means slowly warmed up further and so on. Right. So based upon their respective boiling points. After doing that, if you have any residuals present, those residuals are also removed by passing over calcium carbide to remove nitrogen in particular. Right. So of course we have different methods. One is Dewar flask method, another one is distillation method. So by distillation, generally we separate noble gases. Right. And there is one statement in NCERT that when someone is studying about homosphere of sun, they are able to identify a spectral line which doesn't match with other spectral lines of gases known. So they predicted existence of one more gas in sun. That's why they named it as Helios, right? So name of that scientist is Lockyer, Franklin and Lockyer, I think. Just listen to it and leave it. Discovery of helium. This one. So Lockyer. on a solar eclipse day in 1868 by French astronomer Pierre Johnson and independently by English astronomer Lockyer. While observing sun's atmosphere, they both detected a bright yellow spectral line that doesn't match with any known element. Lockyer, along with Edward Franklin, proposed it was a new element, naming it as helium after the Greek word for the sun, helios. It was not until 1895 that William Ramsay isolated helium on Earth by discovering it in the uranium-bearing mineral cleveite. Right? Responser.
Yes, sir.
Yes, sir.
No. After that, when they are studying the atmosphere, that means the radiation of means the light obtained from sun, they are studying that spectrum of it, right? Along with the sodium vapor lamp. When they are studying the spectrum of it, they isolated a new spectral line, right? So that new spectral line is responsible for existence of another new element, right? And it goes on. That discovery it goes on. Later, Ramsay conducted some experiments. Another scientist by name Rayleigh conducted some experiments, right? So in that way, all the noble gases was found and they are isolated. So that's why I wrote here most of the credit for development of this topic, noble gases, should be given to Ramsay and Rayleigh, right? So we are not bothered about respect to what we got as history, existence, isolation, and so on, right? I think one old JEE question is there in which they asked you some details regarding Dewar flask model based upon adsorption phenomena, right? So that's why I'm giving one brief idea of Dewar flask. Dewar flask is nothing but some capsule-like material, right? So in which we will pass gases, mixture of gases into it, and we will maintain the temperature of it by taking either liquid air and so on. Here I will take charcoal. So when that air is passed in through Dewar flask, based upon the adsorption phenomena, or we will say gases with higher molecular weight will adsorb readily, right? Then remaining gases will be passed through another Dewar flask where temperature is maintained, maybe either liquid nitrogen temperature or maybe liquid oxygen temperature and so on. So in that way, we are going to separate mixture of noble gases, right? So if you want to write one brief way I am writing, I am taking some noble gases mixture along with oxygen, nitrogen may also be present. Nitrogen can be removed by passing over calcium carbide. Oxygen is removed by burning that gases, right? So oxygen will be used up by passing those gases over burning carbon or something like that. So remaining noble gases mixture, helium, neon, argon, krypton, xenon, right? Radon and oganesson, we are not bothered because radon is metal, oganesson is also synthetic metal, right? These gases are passed over the Dewar flask where charcoal is present, right? So I am writing that these are kept in contact with charcoal inside Dewar flask. Different temperature zones are maintained, maybe minus 180, minus 170, and so on. So when we do that, first heavier noble gases gets adsorbed, right? Such as argon, krypton, xenon, right? They are adsorbed over charcoal. At around a temperature of approximately minus 100 degrees centigrade. Remaining gases, helium, neon, they are not absorbed, therefore they are obtained as gases and they will pass through that Dirac flask. Are you able to follow it? Are you understanding this?
Yes, sir.
Respond.
Yes,
So
sir. Yes, sir. Yes, sir.
helium and neon remain unadsorbed. So they are existing as gases only. Now, these gases are now passed over another Dirac flask. Means I will write instead of Dirac flask, I will say charcoal. So it was brought in contact with. It was brought in contact with, or I will say, passed through another Dirac flask. Passed through another Dirac flask, which was kept at around minus 180 degrees centigrade. Maybe some deviation temperature. I'm showing, I'm giving one rough, I understand, right? So which was kept at minus 180 degrees centigrade. Then neon gas will get adsorbed, but helium remains as gas. So here neon gets adsorbed because among helium neon is heavier. So it got adsorbed readily, whereas helium remained unadsorbed. That unabsorbed helium got separated out. Now the neon which got adsorbed, this Dirac flask on increasing the temperature slowly. Now that neon gas comes out, right? So it was evolved in the form of gas and hence we will collect that neon again. So now we have separated helium, neon, and we have one more mixture or one more liquid where argon, krypton, xenon, all the three are present. Now this mixture now brought in contact with, this was kept in contact with another Dirac flask, right, which is maintained at liquid air temperature. Now, at this temperature, among argon, krypton, xenon, among these three gases, which gas will adsorb readily means xenon. Compared to xenon, krypton adsorption is less, argon adsorption is even less. So among these three, when we keep another flask at liquid air temperature, among these three, argon will go into that flask and it gets adsorbed. So you will say argon diffuses and gets adsorbed over charcoal. This on rewarming, if I increase the temperature, this on rewarming, that argon gas gets evolved. So now we have separated argon also. Now this flask is having now two gases, krypton and xenon. Now we have krypton and xenon. Now we raise the temperature of it. raise the temperature of it. So if I increase the temperature of it, among krypton and xenon, which it comes out quickly means krypton will evolve, whereas xenon remains as adsorbed over the surface of charcoal. So raise the temperature approximately to minus 90 degrees centigrade. Then krypton evolves, whereas xenon is up existing as in adsorbed state. On rewarming further, we are going to get xenon also. Is it clear how we are going to separate noble gases? Any questions, sir?
No, sir.
Right?
No, sir.
Sir.
This is one method. We call this method as Dewar flask method. Another method is there, that is fractional distillation method. We call it as Claude apparatus. So that's what we are seeing here. Here we are seeing some distillation, fractional distillation. We call this fractional distillation method as Claude apparatus. Now in this, based upon the boiling points, we are going to separate all the noble gases, right? So krypton, xenon, and oxygen are separated as what we got as one set. Nitrogen, helium, neon is obtained as another content. So as such, we are going to separate them. After them, again by rewarming, we are going to separate it, right? So we will get mixture of different gases. Those will be separated again later on by another method of distillation, right? So better let me write that one point here. One point we need to remember is helium, neon, and nitrogen. These three are obtained as one mixture, right? Obtained as one mixture. So from this mixture, we are going to remove nitrogen gas by passing this mixture over calcium carbide. If I pass it over calcium carbide react with nitrogen to form calcium cyanamide. Calcium cyanamide. Mixture of calcium cyanamide and nitrogen. This mixture is called as a nitrolim. This is how we are going to remove nitrogen, right? To remove the traces of. Then we will have helium and neon mixture. Just this liquid, if I increase the temperature, helium gas escapes out, neon will be condensed out, right? Or we can say by allowing it to keep at a temperature of liquid hydrogen, neon will condense, helium remain as gas, right? And that's how we are going to separate them. This is one fraction. This mixture is obtained as one fraction. Now, second fraction. Argon and oxygen. These are obtained, this mixture as second fraction. Now, from here, we will try to remove oxygen. After removing oxygen, argon is left over. Now, third fraction. Krypton, xenon, nitrogen over, oxygen is over. So these two are obtained as another fraction, right? You may get oxygen liquid also. Krypton, xenon, along with liquid form of oxygen, right? This is obtained as a third fraction. Here, all are obtained as gaseous mixture. I will write as O2 gas, argon gas. So these two are obtained in gaseous form. This is second fraction. Krypton, xenon, and liquid oxygen is obtained as a third fraction. From here, we are going to separate krypton, xenon, and oxygen by doing another distillation method. Is it clear how we are going to separate them? Respond.
Yes, sir.
Yes, sir.
No. So we are now familiar with all physical properties. Ionization energies we have seen, electron gain enthalpies we have seen, right? Abundance is known to us. How we are going to isolate them from atmosphere also we have seen, right? Now, another important point. Uses of noble gases, right? So in that uses, first we will see some important points. If you take minerals like pitchblende, monazite sand, cleveite, etc., these are all minerals of uranium. So we know that all the radioactive elements disintegrate by emitting alpha particles, nothing but helium gas, right? That's why we will write helium, sometimes neon also, sometimes neon are found in minerals of uranium. Or we write as minerals of radioactive elements. For example, pitchblende, monazite sand, cleveite, etc. These are all radioactive metals, right? Now, another important source of helium is natural gas. So we call it as commercial source. So along with natural gas, you will get helium also, right? Now, in this total group 18, xenon and radon, these two are rarest. We will not bother about oganesson because oganesson is man-made element, right? So these are rarest elements of this group. Radium atomic number is 88, mass number 226 radium. This on disintegration. From radium you will get radon, right? 86, 222. Along with that you will get helium 24, right? While you are studying about natural disintegration series, 4n, 4n plus 1, 4n plus 2, 4n plus 3 series. There we discussed one word called gaseous eminent. This is the gaseous eminent. Right? Same way, if you take californium, 98 is 98. Because fermium is 80, no? 98 only. Californium, it is 98 with calcium 2048. I think it is 2040. Gives organism 118 plus neutrons. Right. So organism is up, I think 294. Now try to balance it along with the 294 plus 3, 297. 297 minus 40. Right. Then 240. Then it becomes 80. I think it should be calcium 48 isotope, I think. Calcium 48 isotope. Calcium 48 isotope and californium 249. Then total put together 297. Now it is balanced, right? So californium 98 249 with calcium 2048, you will get organism 294 and 3 neutrons. This obtained organism is short-lived species. So its half-life is milliseconds. Right? So this is about abundance. Now, coming to chemical properties. Chemical properties of noble gases. The existence of compounds of noble gases is based upon ionization energy of oxygen, right? And this credit should be given to Berthollet, right? Due to preparation of one red colored compound of oxygen, right? So all noble gases will have high ionization energy. All noble gases will have very high ionization energy and hence they are not reactive, right? And electron gain enthalpy is also positive. Ionization energy is high, electron gain enthalpy positive. These two are the reasons all noble gases are not reactive. And hence noble gases are less reactive. Right? But one experiment done by Berthollet, I think his name is Neil Berthollet. Correct. Neil Berthollet. Berthollet. Right? So experiment done by Neil Berthollet. Berthollet. 1962. Right? What he observed is, he observed ionization energy of oxygen to form O2 plus is approximately same as xenon to xenon plus, right? I think this value is 1170. Once let me check this. 1170. This is 1175. This is 1170. Right? This is approximately equal to 1175 kilojoules per mole. This is approximately 1170 kilojoules per mole. As these values are close to each other, if O2 plus compound is possible, then Xe plus compound also should be possible. So this is what he predicted, right? So he prepared one compound that is O2 PtF6, where this is O2 is O2 plus, this is PtF6 minus, right? This is the red color compound he prepared. If ionization energies are nearly same, xenon also should form same type of compound, right? Therefore, he tried to prepare same type of compound with xenon. So he made effort to form xenon compound, that is XePtF6. Here also xenon plus 1, PtF6 minus, right? This is also red colored compound. After discovery of this compound, many other compounds are found. After this, many other compounds of xenon are prepared. Right? So the origin is O2 plus PtF6, right? Similarly, krypton also. Similarly, krypton compounds also. Right? The two KrF2. Already we discussed it. With the fluorine and oxygen also only they have been prepared. Right? Similarly, radon also RnF2, which is used in treatment of cancer. Right? And also used in identification of reaction mechanism. We also got as radioactive tracer technique. Right? Now, neon, helium, argon, they doesn't form any true compounds, but they form some type of compounds called clathrates. They are not actually compounds where these gases are trapped inside ice, right? So let me take it as a note. Helium, neon, argon. Krypton is forming KrF2. Xenon is forming many compounds. Radon also forms RnF2 and so on, right? But helium, neon, argon are not able to form any true compounds. So no true compounds are found yet. But they form one type of compounds called clathrates. Right? What are clathrates means? These noble gases are passed through water and temperature was decreasing gradually. Therefore, water converts into ice and these noble gases are trapped inside ice. Right? So we call them as clathrates, but actually they are not compounds. Example, Xe8H2O, I think. It is a clathrate compound where xenon atoms are trapped inside cage-like structures formed by water molecules. So example, Xe.8H2O. Any questions, sir, up to here? Respond. Do you
No,
have any
sir.
questions up to here? Right. Next, sir. Compounds of xenon. Compounds of xenon. Familiar compounds are XeF2, XeF4, XeF6, and oxyfluorides. Now, preparation of xenon fluorides, in which this is very familiar reaction. Xenon, if it is excess in quantity, allowed to react with fluorine at a temperature of 673 Kelvin 1 bar. Very famous reactions are these are three reactions to form XeF2. Another one, 1:5 ratio mixture of xenon and fluorine. 1:5 molar mixture at around 873 Kelvin and 7 bar pressure forms XeF4. Then 1:20 ratio, sir. Xe with fluorine, 1:20 ratio at 573 Kelvin and pressure of 60 to 70 bar forms XeF6. Of course, all these are solids. So this is very, very, very important reactions of preparation of xenon fluorides. Right? Next, here we need to see one note. XeF6 also obtained from XeF4 can also be obtained from XeF4. Corresponding reaction. XeF4 allowed to react with O2F2. Right? So O2F2 is a fluorinating compound. Forms XeF6 plus O2. It is a good fluorinating agent. This is one more reaction. XeF2, XeF4, XeF6, all the three are colorless crystalline solids. And they sublime readily. Approximately around around 298, I think. This one, 298 Kelvin. So sublime approximately around 298 Kelvin. Right? One more important point is there. XeF2, F4, F6. Melting points. One 28.6, 117, 49.5. Okay. Let me see boiling point. One exception should be there. Yes, yes. See this. Observe boiling point. Generally, what we predict? F2, F4, F6. As molecular weight increases, boiling point increases. But observe which is having higher boiling point. Xe F2 boiling point is greater than F4 greater than F6. So another important point. Boiling point Xe F2 greater than Xe F4 greater than Xe F6. Take those values also 155, 117, and 75.6 degrees centigrade. Now see melting point order. Melting point order XeF2, F4, F6. This is also XeF2 greater than, XeF4 greater than, XeF6. Generally, we predict as molecular weight increases, boiling point increases. But in case of xenon compounds, XeF2 melting point and boiling points are greater than F4 and F6. So let me copy that values also 128.6 and 117, 49.5. Wait. Observe that, sir. 117. See melting point and boiling point values of XeF4, right, is the same. They gave one word called triple point. Triple point means a triple point of water also we know now. What do we have triple point?
Sir, all
Where
three
all
states
the
are
three phases coexist, right? Right? Any queries, sir? Do you have any queries? Any questions? Clear
no,
now?
sir. No, sir.
Now, after that, one more important reaction is there. That is hydrolysis reaction. Right? Hydrolysis of xenon compounds means xenon compounds reactivity with water. Hydrolysis. XeF2 reacts with water to form xenon, HF, and O2. XeF2 forms xenon, HF, and O2. In all cases, HF is common, right? HF and O2 also common. But with XeF2, you will get xenon. With XeF6, you will get xenon oxide. With XeF4, you will get both, right? So XeF4 reacts with water, you will get xenon, XeO3 also, HF, and O2. If it is XeF6, you will get XeO3, HF, and O2. 3 means 3. That's all. If I take 3 here, 6 HF. Balanced rating. There is no O2. Is it clear? So these also I will balance. I am taking 2 here. One xenon gone. Means I will write 2 here. Then 4. Then here also I have to take 2. Balance enough. Then in this case, I have to take 4 plus 4, 2 plus 6 and 0. 6 and 0 means 4 to 0, 2. And this is 6 means again 2. Means I have to take it as 3 options should be there. There also must be there. So I am taking 12 here. Then I am taking here 12 HF and I am taking 3. Then I will take 2. Not balancing. Not balancing. Not balancing. Can I take 4 here? 4, 12, 16. 16, 12, 2, no, here also not happening maybe. 16 means I have to take 16. If I take 16, means I have to take 8. Because I am not getting hydrogen anywhere. Only I am getting hydrogen here. Correct? Huh? Means I should take 6 then. 6 means 24. Now I am getting 24. 24 means fluorines balance, hydrogen balance. Now I will balance oxygens. So I should not write more here. So I will write 2 here and 4 here. 6 over. Another 6 are there. So I will write 3 here. Check balance or not. Response, sir. Say something.
Balanced, sir.
Right? Now see this. In case of XeFO4, you are getting xenon and XeO3 both. Means we can consider XeFO4 as combination of XeF2 and F6 also. Right? I am assuming XeFO4 as combination of XeF2 and XeF6 both. Because in hydrolysis, I am getting products which are obtained by XeF6 as well as products obtained from XeF2 also. Now, XeF6 shows partial hydrolysis reactions. Observe partial hydrolysis reactions. So here, XeF6 first react with water to form XeOF4 plus 2HF. This XeOF4 again combine with water to form XeO2F2 plus 2HF. Right? This XeO2F2 again reacts with water to form XeO3 plus 2HF. Right? So during partial hydrolysis, I am getting XeOF4, XeO2F2. During complete hydrolysis, I am getting XeO3. Right? Any questions, sir? Respond. You have
No,
any
sir.
questions?
No, sir.
No. Coming to XeO3, it is explosive compound. So it is a colorless explosive solid. There is not much peculiarity with XeO2F2. XeOF4. This is also colorless but volatile liquid. Right? So this is about partial hydrolysis. In addition to this partial hydrolysis, one more side heading given in your NCERT, fluorinating agents. Right? So I am taking that side heading also. They are all powerful fluorinating agents. Powerful fluorinating agents. I feel like I missed something. Just a moment. So, see this is group 18. Occurrence we have seen 1%, pitch blende, monazite, tribite, all these things we have seen. This table we have done. Electron configuration, ionization enthalpy, atomic radius, electron gain enthalpy. physical properties. They have only this point I missed, man. See, all noble gases are monoatomic, colorless, waterless, tasteless, sparingly soluble in water, very low melting and boiling points, because the only type of interatomic interactions of these compounds is weak dispersion forces. Helium has lowest boiling point, 4.2 Kelvin. It has this point, sir. It has an unusual property of diffusing through most commonly used laboratory materials such as rubber, glass, or plastics. Right? So I'm writing that point also. Helium has unusual property of diffusing through most of the laboratory apparatus like